effectively implement Zeeman terms, artificial Zeeman terms in simulations. In theory, when you think about theories and when you find like good results that basic theory gives, you won't think that when we try to implement, when you try to see that if this theoretical results will give good results in applications as well. So that was one of the motivators that we tried to do, find out when we first tried with SK Hamiltonian, Sherrington-Kirkpatrick Hamiltonians, and then to go for more practical applications like compressed sensor. So the content of this talk is going to be like this. First, I'll introduce the overall idea and what's the problem with that we are dealing with Zeeman terms in Coherent Ising machines. And then I'll go into what are the remedies or the answers that we have found. And then I'll go into a little bit more detail about how we have been able to see that these theoretical results or the SK Hamiltonian results are somewhat consistent when we try to apply that theory to more real-world application like compressed sensor. Right. So for the introduction, in this kind of unconventional computing architecture like Coherent Ising machines and combinatorial, so we think about this kind of Hamiltonian, spin Hamiltonian. Like when we think about Ising Hamiltonians, the theta's would be like this, x, y's, and both Hamiltonians. But overall, what we're trying to do is to find what's the spin configuration that gives us the ground state of this kind of Hamiltonian or energy landscape. So to do this, there have been several simulators and physical machines as well proposed all around the world. Coherent Ising machines, couple lasers, D-Wave as well, and digital annealers, and simulated bifurcation machines, and so on and so on. But in this talk, I'm going to be focusing on Coherent Ising machine specifically. Right, so what is a Coherent Ising machine? So Coherent Ising machine is basically a network of coupled OPOs, DOPOs, digital optical parametric oscillators. And it uses something called a pump gain to find, navigate through this energy landscape. When we think about classical annealing, it uses the temperature as a guide, but in Coherent Ising machines, we use something called pump gain. So in the below threshold of this, low pump powers, there is a just vacuum states, and there is no degree of freedom to consider those as spins. So when you crank up the pump powers at a certain threshold, the system starts to bifurcate, and then we think that considering the minimum gain principle, we think that it will lead us to the ground state of this energy landscape. So now we know about Coherent Ising machines and what's the problem here. In Coherent Ising machines, we try to find the Ising ground state using something called the soft spins. So soft spins, when you think about the Hamiltonian, it's quite the same. But the difference is that when you think about Ising spins, it's binary, -1 or +1. But in soft spins, just continuous values. So the reason these are continuous values is that, we are dealing with the amplitudes of the OPOs. So those are continuous. But the problem arises when you think about a simple problem like this. So let's think about J as this kind of simple 2x2 matrix, and the Zeeman term and the Ising spins. And when you try to calculate the Ising energy, it gives us -1. And if we think about soft spins, it gives a different ground state. This means that we won't find the Ising ground state, but when we try to find it with soft spins, it gives a different ground state. So because of this, what we want to do is that try to diminish this size mismatch between the coupling and Zeeman terms. So that's the basic idea of the problem that we have to solve here. So there are 3 techniques so far proposed to do this. The first one is called mean amplitude. And I'll go into detail about these 3 methods in the following slides. And the second one is called the oscillatory spin. And then the other one is our work, something called Chaotic Amplitude Control based method. Right, so now we know the problem. Now we know what is the Coherent Ising machines and what the problem is as well. And there are three solutions so far proposed. So, and I have to mention here that we are numerically simulating these Ising machines. We are not using physical CIMs to do this. And in current state, in current literature, CIM can be divided into two systems, like the measurement feedback CIM can be divided into two systems, open loop or closed loop. So we are mainly dealing with the closed loop, and I'll go into detail about these as well in the upcoming slides. What's an open loop, what's a closed loop. So in this case, we are approximating the density function of the CIM using Wigner and positive P quasi-probability distribution functions. And we propose a heuristic method as well. Right, so the truncated-Wigner and positive P, the stochastic the approximated stochastic differential equations can be stated like this. And as you can see, these are quite complicated to simulate in a numerical sense. But with these two models, there have been methods, the mean amplitude and auxiliary spins and chaotic amplitude control ways that will propose to deal with Zeeman terms. Let's see what I mean by this absolute mean amplitude method. So as I mentioned earlier, we are trying to diminish the size mismatch between the coupling and the linear part in the Ising Hamiltonian, or when we use these soft spins other than just using Ising spins. So in this case, the authors have tried to just use the absolute mean amplitude to diminish this size mismatch between the coupling. based method has upper hand compared to the previously proposed methods. Right. And when we compare it to the Wigner model and the heuristic model, the evolution, the results are quite the same, but there is some kind of discrepancy in the middle. But I don't think this is very significant in that sense, because this may be due to noise or something like that, because in the heuristic part, there is no noise involved in the heuristic model. So this could be a result of the noise. That's my interpretation of this result. But when we compare to Wigner and heuristics, the results are quite the same for when we increase the Zeeman. All right. So one thing that we have to think about is what happens if we increase the noise inside the Wigner simulations. So that means that when we decrease the photon number, the mean photon number per pulse, the noise inside the CIM increases. So the effect of noise that you can see here, when we have even without the chaotic amplitude control and with chaotic amplitude control, there is a performance decrease in the Wigner model when we increase the G squared value. G squared, when G squared goes up, the mean photon number goes down, and the quantum noise inside the model goes up. So the effect is clear that when we increase the G squared, the performance kind of decreases with chaotic amplitude control. But heuristic doesn't have any of those kind of noise related variables, so it doesn't change, but it needs chaotic amplitude control to boost up its performance. Right, so I think I have a little bit more time. Okay, I'll go very fast here because I think I've used a lot of time in the previous slide. So with those kind of results, we know that we can solve this kind of Zeeman problem with SK Hamiltonians. And now, this is a very real-world application that when we have an initial image and when we kind of undersample it, and in a sparse, when we have a sparse image, we undersample it and we get a lower dimensional representation of the image. So we have less data elements. And when you try to reconstruct it just by using this low dimensional data, what we get is a very noisy image. And to reconstruct it just by using this low dimensional data, what we need to know is where are the non-zero elements in the initial vector. So if we know that, we can solve a system of equations for that and try to get a good reconstruction of the initial. So that's the motivation behind compressed sensing. And this is very difficult in the original formulation L0. So L0 means you have to consider every combination of the sparse vector to get to the point that what's the optimal point that there should be non-zero. So it's a combinatorial optimization problem. Considerably, it's NP hard. So, but L1 is an approximation to the L0. So that means that right now the commercial methods use L1 instead of L0 because L1 is an approximation to the L0 and it's a convex problem. Right. This is just the optimization function and the Hamiltonian. So we did this, and with the same chaotic amplitude control based method, these three. So this BN method I haven't introduced, so just ignore it. But the positive P and the this one, the heuristic model, it gives good results with reconstruction compared to the L1. This L1 is the commercial or conventional heuristic method called lasso. And we have seen that in the heuristic model, even though positive P we have similar 9 equations, so considerably quite complex in that sense, but heuristic just have 5 overall 5 equations, and we can get good reconstruction results, RMC results compared to the complicated models. All right, so another performance equation that we have seen used with the use of this chaotic amplitude control realization method is that when you think about an open loop system and closed loop system, the accurate reconstruction, let's say the area, kind of the optimal eta area, the element regularization term area, quite increased, and it has become wider, and the minimal the accuracy has increased as well. So that's a plus point to using these methods. And finally, the FPGA implementation, we have done using these heuristic methods, we have implemented our models in an FPGA as well. So you can we can kind of simulate open loop, closed loop, and Jacobi. So our methods in the same FPGA system, and by tweaking a little bit more, tweaking the variables a little bit, we can simulate the bifurcation machine as well in the same FPGA. And this is the GIG and everything are continuous variables. And in addition to compressed sensing, we can solve these code vision multiple access problems as well in the same FPGA. So this is the conclusion, and I don't think I have time to go through everything. So this is the end of the talk, and thank you.
Okay, thank you very much. We have time for some questions. Any questions on this presentation? This question here, yeah.
Thank you for the nice talk. The chaotic amplitude control uses some feedback. So, do you have any idea to implement such method using such a feedback to the actual physical closed version of CIM?
Right now, the physical CIM doesn't have any amplitude control going on, but right now, to my knowledge, the chaotic amplitude control has been implemented in FPGAs mainly. So I'm not quite sure because I'm not a physicist. I don't know what will be the specific specifications or what will be the specific requirements to implement in the physical CIM. But as far as I know, there hasn't been any implementation of chaotic amplitude control in the physical CIM.
Thank you.
Any additional questions? Maybe on a related topic, I mean, if you have the opportunity, will you have the opportunity to run these sorts of ideas on an actual coherent Ising machine? And if so, how might it differ?
Well, I mean, the one of the problems that we have is the precision of the variables that we simulate. Even with the FPGA implementation compared to the GPU simulation that I have done, when the precision of the floating points differ, the accuracy kind of has a fluctuation going on. So more the merrier in that sense. So if we can represent more floating points in the simulation, that would give us quite a bit more accurate results. But in the current physical CMs, there is I think it only has 16 or something, 16 or 9 bits going on. So there is somewhat of a long way to the physical CM to catch up for I think for accurate quite exact simulation of what we have done. But it's a possibility, yes.
Okay, well, in the interest of time, perhaps let's thank the speaker again and move on to the next presentation. Thank you, Sudeera.